Good afternoon, everyone. Welcome to Finite Element Method. Of course, it's week 4 today. So, our live session will be going on from 3 to 5 p.m. In last few couple of live sessions, we saw the basics of the finite element method, and then we also saw the approximate methods, how approximate methods are useful in solving boundary value problems. Out of approximate methods, we saw the weighted residual methods, and then we saw one more important method, that's the variational method or Rayleigh-Ritz method. In last week, we discussed that one. So actually, Rayleigh-Ritz method lays the foundation of the finite element method or the basics of the finite element method that we are going to study today. So continuing from the last topic, if I move to the last week slides here in the Rayleigh-Ritz method, what we use it to do is that we applied variational calculus to our boundary value problem here, like variational calculus to our boundary value problem, and then we use a different variational identities to come up with a function. Where was it? Like this function, to come up with a function like this, which we known as functional. In last class, I hope you all people remember this functional. We then use it to minimize with respect to the unknown parameters and the get the value of those unknown parameters that we have assumed in our trial solution. I also mentioned you in the last class that the accuracy of our solutions, that is the closeness to our exact solution, depends upon the number of unknowns or the degree of the polynomial that we choose for our this approximate solution. So continuing on that line only, today we will be seeing the basics of the finite element, basics basic concepts of the finite element using that Rayleigh-Ritz method. How with the help of Rayleigh-Ritz method we will be able to develop a formulation for finite element method. So if you look into the name itself, it starts with finite element. It means that for a given problem or for a given domain, there is something very finite. So finite element method, as I also already explained it in the first introduction lecture, that finite element method is just breaking the bigger problem into smaller domains, and then solving our governing differential equations in smaller domains and getting the solution for all of our domains. Same concept I will be repeating today. Like for example, if we have a plate like this, bigger plate like this, it was having some boundary conditions applied, like it was fixed from one side, and then some force was being applied from one side, that is pull was being applied from one side like this. So for this we had conventional plate equations or the governing differential equations that we can solve and can obtain the solutions using conventional methods as well. But I told you the beauty of the finite element method is that it incorporates complex boundary conditions, it incorporates complex geometries, it incorporates the complex material transformations that occur inside our domain, so that we can use the numerical method, that is finite element method, to solve these boundary value problems or the governing differential equation that we have. Else it was not possible using our conventional methods to solve them. So what we do in this finite element method, we break this problem into smaller elements like this. For example, if it is a very thin shell, we use shell elements. You will learn in the coming classes what are shell elements, what are solid elements. For time being, you just keep remember it. We will use very small shell elements like this. We divided our problem into very different small domains, and then same we were having one governing differential equation that was being applied to this whole domain. But what we do, we will take the same governing differential equation and solve it for one small element. And then for that small element, we can obtain the different solutions. Like in finite element method, we assume the unknowns to be these nodal parameters. Like these are called nodes, as I already mentioned in the last class. These nodal parameters like 1, 2, 3, 4, 4. We obtain these nodal parameters, and from those nodal parameters, we post process those nodal parameters. Like in last class, we obtained the displacement. Post processing this displacement, we will obtain the strain. Then from strain, we will obtain the stress. From stress, we will obtain the force. I clearly mentioned in the last class how from the small one field variable we can obtain the different things. Like in it's not only displacement will be the field variable in every each and every problem. It depends upon the type of problem we are solving. For example, if we are solving thermal conduction problem or problems like that, there we have a field variable like temperature. From temperature we can obtain different things like heat flux and other things as well. So starting from the last class, today we will be seeing what will be the basics of this finite element. For example, initially we will not be considering these types of domains like square this planar domains. Like initially we will be studying these line problems only, in which the elements will be aligned along 1D, or we call them as 1D elements along line only. So what we do that, for example, this is our problem domain from 0 to something, it runs up to x, and we will divide this problem into smaller number of elements with nodes 1, 2, 3, 4, and so on, so 4, and so on. And then subsequently, this will be our element 1, this will be our element 2, this will be our element 3, okay? And we will solve the differential equations for one single element and obtain the solution. And since this is a repetitive process, solving same governing differential equation for another element like this, that's why this method is very popular. Like we have to define the formulation for only one element, then as it's a repetitive process, then we can write a computer code for this and then can give it in the form of a software. That's why this method is very popular. So what we call these things as, these are known as elements, and these are known as nodes. Okay, these are known as nodes. Then here there will be somewhere here there will be m minus 1th element, and there will be node like n minus 2th node, n minus 1th node, up to nth node. Okay, like this will be nth node and it will be mth element. I hope you people are getting my point. This and this. So let's consider one typical element. One typical element will be which will be generalized throughout the domain like this. Let me consider one typical element. Considering typical element. Okay. For example, this is our line 1D element like this. It is having nodes. Okay, this is our typical element. Like for example, its one node is at x comma xi, and another node is obviously will be xi plus one. Okay, because node numbering has been done continuously. And let its length be li. Okay, it's ith element. Okay, moving forward, let me write for you people here what was these all things in the previous diagram that I showed here. It was m was number of elements, and then uh, n was total number of nodes, where xi that I assumed here to be xi is x coordinate of node I. Okay, coordinate of node I, comma li, length of element I. Okay, length of element I. Okay, now we will be, while I am teaching you this concept, we will be parallelly solving one general boundary value problem also. Let me write that problem for you as well. That problem is, we will be solving this problem today. We have u double dash of x plus x square is equal 0, and its domain is 0 less than x less than 1. This is our problem for governing boundary value problem for us today. Okay, where we have it's this boundary conditions are u of 0 is equal to 1, and another boundary condition, that is this boundary condition, natural boundary condition, plus 2u1 is equal to 1. Okay, so these are the two boundary conditions that this governing differential equation has to satisfy, or the boundary value has to satisfy. So one more thing I want to mention here is that from the last class I showed you how to obtain functional from given a differential equation. So I will not repeat all the steps again. I will directly write the functional for this boundary value problem. Please go back to the last lecture and see how this has been calculated. I will be directly writing the functional. Functional will be 0 to 1 minus 1 by 2 u dash square plus x square times u and integrated with respect to dx plus first boundary condition u of 1 minus u square of 1. Okay, please see the last class to see how I come up with this functional. Okay, this is functional. Then moving forward, now for this typical element, as I already told you, I told you why this approximate methods is important, because again for this typical element we have to assume a solution. We have to assume a solution, and then which will be as a function of some unknown constants, and those unknown constants we have to find out, keeping in the mind that the error between the exact solution and this assumed solution should be as minimum as possible. That is the basics of this finite element. So for this typical element, we will assume a linear polynomial as trial solution over the element. Okay. So for this element again, I will take. So again, I will be needing it everywhere. So I will be taking it my paste. So what is the basic concept here is, here again, what we have to do, assume trial polynomial. Polynomial. Okay, we assume that trial polynomial. It will be function of unknown unknowns. Find unknowns. Okay, but we have to find unknowns keeping error minimum as possible. This is the basic behind this finite element. Assume trial polynomial, then which will be the function of some unknown constants. You have to find those unknown constants, and those unknown constants have to be found to be in such a way that the error between the exact and the assumed solution should be minimum. It is like this, then it goes to this step, then it goes to this step. Okay, so for this typical element we will assuming for this element we will assume linear polynomial. So in the last problem we assumed a quadratic polynomial, a naught plus a1 plus a1 x plus a2 x square, if you people remember. So assuming, so yeah, it also depends upon what degree of polynomial you are choosing. So if you are choosing a polynomial with higher degree, you will get an solution which will be more closer to the exact solution. If you are taking a very less number of the unknowns, or in other words, you are taking the less degree of this polynomial or trial solution, you will get a you will not get that good result, and it will not be exact, not matching with the exact solution. So the degree of the polynomial or the number of the unknowns play an important role in the accuracy of the final solution. Assuming a linear polynomial, okay, so linear will be in the shape form of this a naught plus a1x, okay. So and its domain will be like it's obvious from the figure, domain will be xi less or equal to x less than or equal to xi plus 1, okay. It will be like this. And so if we put xi here, u of xi will be equal to ui. So value of trial solution or the linear polynomial at xi node will be ui. So its value, nodal value will be ui. It will be ui plus 1, okay. You keep this in mind, okay. And it will be equal to a naught plus a1 xi. Similarly, u of xi plus 1 will be ui plus 1. So it will be a naught plus a1 xi plus 1. Okay. So these are the two important equations we have to keep in mind. Then if we see, this is equation first, this is equation second. If we do subtracting second from first, okay, what we have, we will get ai to be equal to, if you perform the steps carefully, you will get ai to be equal to ui plus 1 minus ui divided by xi plus 1 minus xi equal to ui plus 1 minus ui. So let me denote this xi plus 1 minus xi will with li. Obviously, it is a difference between two coordinates xi plus 1 minus xi. It is equal to the length of element li, okay. So it will be li, okay. Then when we substitute back this ai in first equation, substitute ai in equation first, okay, then we will get the value of a naught. So both unknowns are known now. A naught to be equal to ui minus ui plus 1. You have to see all the steps at your place carefully, okay. ui, I'm writing the steps directly because otherwise it will be a long process to solve the steps one by one. Xi plus 1 minus xi, okay, times xi, okay. This, if you carefully see, a naught will be equal to ui xi plus 1 minus ui plus 1 xi divided by li, okay. Then if we will combine both the solutions and substitute this in original equation, that is equation a, okay, we have equation a because we got the value of a naught and a1 as well. A this one, this is here like this, and we got a naught to be equal to, this is a, this not ai, this a1, this is a1 here, sorry. We got a1, we got a1 here like this, and a naught here. Mm, Substituting a naught and a1 in equation a, we will get uh, we will get total the trial solution that we assumed u of x to be equal to, I will write the general form to be like this, xi plus 1 minus x divided by li Li times ui plus another thing will be minus xi plus x divided by li times ui plus 1. Okay, so let me define. There are some constants here. Let me define those to be ni to be equal to xi plus 1 minus x divided by li, and another one ni plus 1 to be equal to minus xi plus x divided by li. Okay, then my solution will be equal to u of x will be equal to ni ui plus ni plus 1 ui plus 1. So we defined something, two different things, ni and ui. Actually, these ni and ui are known as shape functions, and they are defined at respective nodes. These are shape functions. Okay, so like shape functions have a very important role to play in deciding the solution within an element. So for example, if we have the same element like this, we have this same element like this, we have this element. So it was like it was having one nodal value ui here and ui plus 1 here. So we defined one more quantity ni and ni plus 1 here as shape functions, ni, and this is ni plus 1 here. Okay, so these shape functions, actually if you see the term itself, these shape functions interpolate the values of these nodal values, interpolate these nodal values within this rest of the domain or the rest of the element, or it shows the influence of these nodal parameters or the nodal values on the rest of the solution within the element. I hope you people got this point.
Sir,
Yes,
what is the meaning of shape function?
I'm explaining the same thing. No, like we define it here, ni to be xi plus 1 minus x divided by li, and another for another node. This ni defines that how this nodal parameter, that is ui, will have an influence on the rest part of the solution. So we have to find the solution at other points within the element. No, like this. It shows that how this, what will be the shape of the function, or what will be, if we plot the function, how its shape will be, it will be decided by this shape function only. And it is influence is like, if I will be plotting the graph of these shape functions like this, how they influence, or how they show the effect of this nodal parameter on the rest part of the solution. For example, if I plot ni, like it's for I, it's I plus 1. If I see the value of I, it is here xi. I hope you people remember this is xi plus 1. So the value of ni for this node, that is ni, I have to put x equal to xi. So if I put xi here, ni will be equal to xi plus 1. Here, this equation. Put x equal to xi minus xi divided by li. So initially I told you that xi plus 1 minus xi is itself equal to li, length of element, divided by li equal to 1. So if you see that the value of this shape function at the node itself is coming to be equal to 1. So its value will be equal to 1 on the node itself. And if you put x to be equal to xi plus 1, put here x to be equal to xi plus 1, it will come out to be 0. So like it's, and the function x is linear in the shape function itself, so it will be linearly decreasing like this. So at this it is having value 1, and at another node it's having value 0. So it shows that how this nodal value, that is ui, is going to contribute to the other part of the solution, like at other points. Sorry, once again. So it shows the what will be the influence of this nodal parameter on the rest part of the solution, or it just interpolates the solution within the domain. So if we see the value of this u of x, how it is, u of x is like this here, u of x is here. So I will be taking this u of x again. So our u of x is this. So if we see within this typical element how this u of x is varying, so our element was like this. This was this was ith node, and this was ith plus month node. And so the value of this solution, u of xi is equal to ui. So the nodal value was here to be equal to ui, and the another value was here to be, let me take this element to be here up to this point, I plus 1, and then I will show you to how it can be interpolated to another element I plus 2. Okay, and then this is continuing from this side as well, and this is continuing from this side as well. We have taken this generalizer from some problem. Okay, so this will be I plus 1. It is ui here, and at u solution at x point xi plus 1, it will be equal to ui plus 1. So this nodal parameter is ui plus 1. ui plus 1. You will be seeing that x is everywhere linear, so it's easy to plot in between these two values. It will be a linear function like this. So you can see that how our u of x is varying within two nodal values ui and ui plus 1. And then this can be continued to another this, I mean to say, the node where the nodal value will be ui plus 2. So it will be continuing like this. Okay, this will be here. You can see that at the junction of the two elements, that is element I. So remember, I am writing the node without n circle and element with a circle. Okay, I plus 1, I plus 1th element. Okay, so here we are having a common node of two elements. So this is important, that the value of this node when evaluated within this element is equal to the value of the nodal parameter when evaluated within this element, to maintain the continuity of the solution. Otherwise, there will be a discontinuity in there. Same thing we can plot with for the derivative, first derivative of this solution. Like this is a linear function, so its derivative will be a constant function. Okay, I hope you people know this thing. So directly, its derivative will be a constant function. So uh, I don't know the value of that derivative, so let it be like this. Up to this point, it will be a constant function like this. So let this derivative will be, it will be the derivative. So this value will be dou u of x. So it's a function dou u of x with respect to dou x. Okay, and it's the value of the derivative in element 1. So it's node I again. It's node here I plus 1, I plus 1, and then similarly in the node second, element second, sorry, it will be something little bit higher like this. So this value will be, it will be dou u of x divided by dou x within element 2. So sorry, not element 2, it will be I plus 1th element. This is again I element, this is I plus 1th element. So this is ith element, this is I plus 1th element. So this derivative of this trial solution is very important because we require in require the most of the times we require this first derivative in computing the other quantities. You might be having a question, what is the example of that? Like in the last class I showed you, we computed the displacement at a node. Then we needed to compute the strain. So the strain is the first derivative of the displacement with respect to the x. That's why in every problem I am showing you the solution as well as its derivative. Then there are other higher quantities which we can plot, like we have curvature, then again we have moment and other things. Those are the some other higher derivatives of the same displacement. So important is first we see how the displacement, this derivative of the first derivative of the trial function is varying. Now what we can do is that we can solve the same functional, the functional that we have this for this problem here, this functional. We can solve this functional within the domain itself. Okay, small domains, and then we can obtain the value of all the nodal parameters, that is ui plus 1, ui plus 2, and then we can interpolate within the function with the help of the shape functions to see the variation of this solution. So how we can obtain the solution, like, so we know that the appropriate functional we earlier saw what it will be. So we can solve the functional total functional for the problem. First, let me write the functional again for this small element. This is a functional for our differential equation. This is a functional. So let us denote this whole quantity to be equal to, let us denote this quantity to be equal to f. Okay. Then we can write the functional for all the elements to be equal to throughout the domain, functional I of u for one element. This is for whole problem we can write the functional. We have to just integrate it throughout the domain and split the integral to be within different elements. X1 to X2, we denoted this by f dx. Then for another element it will be X2 to X3, as the element numbering is continuous, f dx. Okay. Then continuing up to nth element, f xn minus 1 up to xn, f of x dx. And these boundary terms will be always there, u of 1 minus u square of 1. So these boundary terms will be either on the first element or the last element. So you need not to consider these boundary terms within the middle of the elements, because there is no point or there is no sense of using these boundary terms within those elements, because they are not at the boundary elements. Boundary elements will be either first element or the last element. So I can write this will be the functional. This is functional for whole element, for whole problem with n elements. Okay, I hope you people got this point. So let us solve the same differential equation with choosing the different number of elements. So let us see if we choose only one element. Okay, one element solution. First will be one element solution. So for this one element solution, so the entire domain will be considered to be one element. So our domain was 0 less than x less than 1. So this will be totally distributed within one element. So our x1 will be equal to 0, x2 will be equal to 1. And the length of the element will be L will be xi plus 1 minus xi, where I is equal to 1 and I plus 1 is equal to 2. It will be 1 minus 0 will be equal to 1. Okay, length of element li. So the nodal parameters in the problem will look like this. This is x, okay. X is varying like this. So this is x1 is equal to 0, x 2 equal to 1, and this will be the nodal parameter u1. This will be u2, okay. The trial solution is, as I already showed you, how we write the trial solution in the form of functions to be n1 nodal parameter u1 plus n2 nodal parameter u2. Okay, where n1 has uh, equation to be xi plus 1 minus x divided by li. Here this is xi, this is xi plus 1. Now you all, and this is li, okay. You put the values, you will get it to be equal to x2 minus x divided by L. X2 is equal to 1 minus x divided by 1 is equal to 1 minus x. Similarly, N2, that's Ni plus 1, you can write it to be equal to, similarly following this procedure, x1 plus x divided by L. Okay, it will boil down to x value, substitute all the values. So our trial solution therefore becomes u of x becomes equal to 1 minus x times u1 plus x times u2. This is our equation 1, okay, in this problem. Don't confuse it with the previous equation number 1. And we also have the boundary conditions given that we are given that u of x is equal to 0 equal to 1. That means which is u at x equal to 0 is equal to u1. That is u1 is equal to 1. Putting u1 equal to 1 here, we will get u of x to be equal to 1 minus x plus x times u2. Okay, this is the thing. And u dash to be equal to minus 1 plus u2 if you just differentiate this function. Okay, as I already wrote, the functional for this problem I of u is given as integrating over the domain 0 to 1 minus 1 by 2 u dash square plus x square u integrate dx plus boundary terms u of 1 minus u square of 1. Continuing, and if you remember u of 1, okay, what is the value of u of 1? U of 1 is actually u2, isn't it? Like this is x2 equals 1, so u of x is equal to 1 is equal to nodal parameter u2. Okay, substituting this to be equal to u2 and other things as well, our functional boils down to I of u equals 0 to 1. This is u dash minus 1 by 2 u dash is equal to, we found u dash to be equal to minus 1 plus u2. Okay, minus 1 plus u2 o square plus x square times u was to be equal to 1 minus x, 1 minus x times plus x times u2. Okay, and we will close this integral dx and plus u2, this is this u2, okay, plus u2 minus u2 square. This is again u1, it will be equal to u2, putting u2. Okay, if you carry this whole integration, because There is only one parameter x. You have to put it first integrate and put x equals 0 and x equals 1. Your functional will boil down to I of u to be equal to minus 5 by 12 plus 9 by 4 u2 minus 3 by 2 u2 square. So there is only one unknown u2, and the necessary condition for the error to be minimum is, or minimizing, I of u2, it's a function, I of u, it's a function of this, then its partial derivative with respect to u2, I by dou u2 should be equal to 0. When you carry out this integration, you will get u this differentiation on this and then put equal to 0. You will get u2 to be equal to 3 by 4. So your solution then becomes u of x becomes, first is 1 minus x, then u1 plus x times u2. Put both, u1 is equal to 1 and u2 equals 3 by 4. Your solution for the one element solution for this problem will become u of x to be equal to 1 minus x plus x times 3 by 4, which boils down to be u of x to be equal to 1 minus 0.25x, and your u dash to be equal to u dash of x to be equal to minus 0.25. That is the one element solution for this problem. Okay. And you can plot the graphs for these as well. So u of x will be like this. It will be negative. It's having a negative slope like this. This is u of x, and its derivative will be negative like this. This is x, this is y, this is x, this is y, and it will be a constant value of 0.25 minus 0.25. Okay, minus 0.25. It is u dash of x. I hope you people got the point. So if you will use two elements for the same domain, now continuing it to second two element solution. Okay, two element solution we will see. We will see how using more number of elements, how much the accuracy of the solution will improve. That's our point only. So we have the same domain like this. We have here equals x1 equals 0, and then we have, it will be now here x3 equals 1, and middle we will be using two elements of equal length, x2 to be equal to 0.5, because we have total domain 0 x1. Okay, then now there will be three nodal parameters u1, u2, u3, three nodal parameters, and let this would denote to be denoted as element 1, and this to be denoted as element 2. Okay, there is nothing, and the variation is along this x is this. And we already know that there is an essential boundary condition, that is u at x1 is equal to 1, or which in other language means u1 equals 1. Okay, now we will see the solution for first element. Okay, element first. Okay, so for the element first, the domain will be 0 less or equal to x less than 1 by 2. Okay, this is the element first domain. Okay, so if we compute the shape functions for this element similarly, like we did in the previous section, like we had shape function n1 and n2, you have to calculate n1 and n2 quickly. So n1 will be equal to x2 minus x1 divided by L, and this will be equal to 2 0.5 minus x. You people check this at your place. And similarly n2 will be equal to minus mm, x1 plus x divided by the length of element. Length of element is, remember, length of element is equal to 1 by 2. Is this is equal to L equals 1 by 2. Okay. So we got this to be equal to x, okay, because x1 is equal to 0. This is equal to x, okay. So our solution for element 1, u of x for element 1 will be equal to n1 u1 plus n2 u2. Then u of x for element 1 to be equal to, it will be twice 0.5 minus x plus 2x, okay. And u dash will be equal to, computer's derivative, it will be minus 2, I think, plus 2u2. Okay, this is u2, sorry. Okay, these things we computed for element 1. Similar things we have to compute for element 2. Quickly, one more thing, one second. Okay, for element 2. Okay, element 2 we have to see which varies from 1 by 2 less than x to the end part of the domain, that's 1. Okay, for quickly, for this shape functions will be n1, I will directly write what will be the shape function n1, 2 1 minus x, and n2 will be equal to 2 times minus 0.5 plus x. You check these things at your place. And u of x will be equal to n1 u1 for element 2, okay. So its u1 will be then u2, okay, u2 plus n2 last nodal value u3, okay. U of x for element 2, for element 2 comes out to be twice 1 minus x, put this value here, this value here, twice x multiplied by u2 plus twice 0 minus 0.5 plus x times u3, okay. And sidewise you compute its derivative as well because it's required in functional. This not square, don't, this is for element second, this is one also. So its derivative will be minus 2u2 plus 2u3, okay. So I already told you how to write the functional, like here. Functional will be split into different functionals for each element, okay. And the functional will be obviously same, but the nodal parameters will be different. So we have to write the functional for the problem will be total functional I of u will be functional writing for the first term, and it varies from 0 to 1 by 2, and our functional will be again same, minus 1 by 2 u dash square plus x square u dx, and second will be from 1 by 2 to 1, 1 by 2 to 1, and it will be minus 1 by 2 u dash square plus x square u dx, and there will be boundary terms like u of 1 minus u square of 1, okay. You have to use appropriate u here, appropriate u here. This is for element first, this functional, this is for element second, this functional, okay. So you have to properly use this u of x and this u of x there, okay, for 2. Once I will put, okay, once I will put all these things in the appropriate functionals, appropriate u of x is in the appropriate functionals, I will get the long interval 0 to 1 by 2 like this, minus 1 by 2, this is for first element, remember. So for first element, u dash of x is equal to minus 2 plus 2u2. Let me show you people also. U dash of x equals minus 2 plus 2u2, and in the function it's squared, okay, plus Then we have x square times u of x. So functional for u of x for the first element is 2y 0.5 minus x uh, plus twice u2, okay, d of x, okay, then plus 1 by 2, this is for second element, okay, 1 by 2 to 1, then functional term will be minus 1 by 2. Now it will be its u dash of x. U dash is equal to minus 2 u2 plus 2 u3, okay, minus 2 u2 plus 2 u3 square plus x square times the u of x in element second. U of x in element second is given by this equation. It is twice 1 minus x times u2 plus twice minus 0.5 plus x times u3 bracket close dx, and there will be boundary terms. I already told you here the boundary term is where we wrote. Boundary term is this is u of 1, u of 1 and u of 1 square. So if you see u of 1 here in the problem, this is u of x is equal to 1 is equal to u of 1, okay, and its nodal value is u3. So put appropriate terms there. So it will be plus u3 minus u3 square, okay. When you will carry out this whole integration and put the proper limits, we will get the functional to boil down to this equation. I of u2 is equal to 1 by 96 taken outside minus 95 plus 206 u2 minus 192 u2 square plus 113 u3 plus 192 u2 u3. It's a long expression. I recommend you to solve these integrals using MATLAB or Mathematica. 192 u3 square, okay. So now you can see that we are having two unknowns u2 and u3. So the necessary condition for minima is, what is this minima? This is the necessary condition for the error to be minimum, okay, for the minima of I of u, or in basically it is the minimum error to be minimum. We have necessary condition, it is partial derivative with respect to first unknown I u2 should be equal to 0, and with respect to another a3 it should be equal to 0. When you will carry out these two things, you will get the expressions like this: 103 divided by 48 minus 4u2 plus 2u3 equal to 0. You will get this one linear equation in u2 u3, and this will give you 113 divided by 96 plus 2u2 minus 4u3 to be equal to 0, okay. When you will solve these two simultaneous equations, you will get u2 equal to 0.9115 and u3 to be equal to 0.75, okay. Then so the element solution, we got the u2 u3, okay, we got the u2 u3. So for domain 0 less than x less than 1 by 2 or element 1, we got uh, u1 is equal to 1 and u2 is equal to 0.9115, 0.9115, okay. Then we can write u of x in element first to be equal to which we calculated earlier in element 1 to be equal to 2y 0.5 minus x plus 2y x u2, okay. So if we put u1 and u2 values in that, I will get u of x for element 1 to be equal to 1 minus 0.177x. Remember, this is for element 1, and its derivative u dash of x will be equal to minus 0.177. This is for first element. If I carry the same operation for second element, its domain is 1 by 2 less than x less than 1, element 2, okay, element 1, okay. So for that, u of 1 is equal to 0.9115. You are getting my point. This is u2 for element 1, but this is u1 for element second, 9115. And u3, u2 is here for element second is the global u3 to be equal to 0.75. It is u2 for element second and u3 for element second, okay. When you will put these values, you will get u of x within the element second to be equal to 1.073 minus 0.323x. You remember which expression for u of x you have to use in element second? Element second, you have to use this expression, okay, and derivative you have to use this, and u dash of x will be equal to minus 0.323. So this whole thing is for element second. Now we have to just plot these values to connect this. So for like this will be again negative values only. So for element 1, it will be negative going down slope like this. Then this line is having more slope. Here there is 0.32 and here is 0.177. So this is having more slope. You can see that u of x. This is u of x. This is x. And if we will try to plot the derivatives as well, we will see that the derivative varies like this. First for derivative is minus 0.177 like this for first part, then it is minus 0.33 like this. This is u dash of x. This is x varying like this. You can see that the accuracy of the solution is a little bit, first it was like straight line only like this going, then now it has improved. Now if we increase the number of elements, increase, kept on increasing, there will be one point when this line will be exactly matching with the exact solution. That's the beauty of the finite element. So in today's lecture, you people got to know about the basic finite element, how we discretize the domain, and how we develop the shape functions for linear elements. Using those shape functions, we simultaneously solved one numerical problem where the boundary value problem was given by this boundary value problem. Okay, this boundary value problem we solved, and we obtained it as one element solution and two element solution as well. I hope this session was beneficial for you people. Thank you everyone for joining this session.
Okay, thanks. Yeah.
Thank you.